Hello everyone, I am a master's student at Jilin University. Now, I will be presenting our paper Rethinking Glyph Spatial Information in Font Generation. Font generation is a specialized subset of image generation tasks. I will present our work in three parts: the background, the methodology, and the results. First, let me give you a quick preview of the background. A content image indicates which character to generate, while reference images indicate which font style is needed. There are a few reference character images and one content image. Few-shot font generation aims to extract the font styles from these reference images and apply them to the content image. We treat glyphs as spatially constrained objects rather than coordinate-free textures as in previous typical FFG methods, and then propose improvements regarding data pipeline, dataset, and model. First, we propose the SPR scheme to establish a unified rendering to vectorization pipeline. Second, we introduce a large-scale Chinese font dataset to build a unified benchmark. Finally, we develop Glyph SpatialNet, a two-stage decoupling architecture to achieve SOTA performance. We propose the spatial preserving rendering scheme, a unified method that systematically eliminates spatial bias and enables accurate vectorization for end-to-end automation, resulting in usable TTF font files. Essentially, it establishes a reversible mapping between vector font coordinates and pixel image coordinates within a certain tolerance range. While establishing a unified data pipeline, it also facilitates model training. Copyright restrictions force most methods to use their own private datasets. Existing datasets are low quality, degraded into texture images, and cannot be recovered as font files. Unlike existing distorted rendering datasets, our vector source files offer higher flexibility, furthermore support vector-driven models, and enable future exploration. And the OFL license allows free use, modification, and redistribution for academic purposes. We collected open-source Chinese fonts licensed under OFL from GitHub and Google Fonts. All 222 fonts we gathered cover GBT2312, a standard that includes 6,763 simplified Chinese characters, and together they yield a dataset containing 1.5 million glyphs. In terms of model, we developed the Glyph SpatialNet, a novel two-stage decoupling architecture that enables efficient and high-fidelity font generation through spatial modeling. In training, our model has two stages. Stage 1. We train the process of font style transfer to generate low-resolution target images for efficiency. An average conditional mechanism is applied in high-resolution pixel space for flexible style conditioning. B. We incorporate our SPD architecture into the reverse process of a diffusion model, which we call the SPD reverse process, to reduce the coupling of shape artifacts and positional bias during training. This step is carried out in low-resolution pixel space to lower computational complexity. C. Our GBM addresses the gradient locality issue in bilinear sampling, allowing the position path to effectively correct large spatial bias. Stage 2. D. We freeze the style encoder and train the SDE to preserve fine details while generating high-resolution images. During inference, we combine the components of both stages to obtain high-resolution target images. We compare our method with several SOTA font generation approaches. Our model achieves SOTA without requiring component labels, offering better usability and flexibility. The training data is rendered using our SPR scheme on our dataset, establishing a unified benchmark for SOTA methods. We also compared the impact of the current mainstream rendering method and the rendering method of our SPR scheme on model learning. The quantitative evaluation of font generation models under original rendering versus our SPR scheme, demonstrating SPR's capability to enhance model learning and boost generation performance. For each metric pair, the left black number denotes the result under the original rendering, while the right one is produced under the proposed SPR scheme. Red or blue color indicates the metric is increased or decreased, respectively. Spatial noise acts as a regularization term for GAN-based models, but as noise for diffusion-based models. When spatial noise becomes the principal contradiction, the SPR scheme yields remarkable gains. We compared the visual appearance of the results from these methods. GAN-based methods tend to produce noticeable stroke errors on unseen characters. Although MSD font can generate visually appealing images, encoding glyphs into latent space results in blurring when handling complex structures. We avoid such blurring by maintaining entire generation process in pixel space. We also illustrate vectorization results across different resolutions. The 128 squared resolution is sufficient to validate the effectiveness of our proposed approach, because the vectorization error is sufficiently low at this resolution. In the future work, we will continue to apply the idea of glyph spatial modeling to more complex tasks. Thank you for listening to my presentation. If you have any questions or are interested in our research, please feel free to contact us.